Hello everyone, welcome to another EMS webinar. My name is Mihailo and today I'll be talking to you about simulation of magnetic gears in EMS for SOLIDWORKS. Before we start, let's have a look at our agenda for today. We're gonna, for those of you who are not very familiar with EMS and its solvers, we're gonna start by a short overview of EMS, what it can do, what kind of solvers does it contain, and so on. Then we're going to proceed into a small introduction into magnetic gears and what they are used for, how do they work, and what kind of different results you would want to look in when doing a design and simulation of a magnetic gearbox. So then we're going to move into EMS and show you how to set up an analysis of a gearbox in EMS and how to get those results that you're looking for. We're going to wrap up this webinar by a short questions and answer session. However, if at any point during this talk you have something to ask, feel free to type it in the chat box. And at the end, I'm going to do my best to answer your questions. So, as you probably know, EMS is a CAD embedded electromagnetic finite element method solver. So, what EMS does, it allows you to remain within the boundaries of your favorite CAD environment and do both modeling, design, but also simulation, performance evaluation, and so that you can easily go back, change some things in your design, and easily optimize your systems without having to use different platforms. EMS electromagnetic solvers can be roughly grouped into two categories. The first one are electric and the second one are magnetic solvers. The electric solvers are of three kinds, and the first one would be the electrostatic one, which allows you to simulate electric fields and associated phenomena such as electric force, dielectric breakdown, capacitance matrices. All of it you can compute by using EMS electrostatic solver. A typical application of the electrostatic solver would be high voltage insulation. You can analyze electric field. You can see if your system is actually going to remain within the boundaries of dielectric integrity. In case you were dealing with electric fields which are of sinusoidal nature, which change in time in a sinusoidal manner, in that case you would probably want to use AC electric solver, which allows you to compute all of the results and values you can get in the electrostatic module, but at the same time you get this dynamic aspect of results. It's a frequency domain solution, so you can also compute stuff like dielectric losses that come with the changing magnetic electric field. Finally, the last electric solver would be electric conduction. This one allows you to compute steady-state DC current distribution in your parts, and a typical application would be a fuse design. Magnetic solvers, there's also three of them. The first one is magnetostatic, which allows you to compute magnetic fields and all of the stuff that come with it, such as torques, forces, inductances, conduction losses associated with steady-state DC currents. So all of these results you can get for a situation where you have a steady state, unchanging in time magnetic fields. For those cases, you would use magnetostatic solver. In case you want to analyze an AC current source and all of the stuff that come with it, then you would go with AC magnetic. The stuff that you get with AC magnetic in addition to magnetostatic would be eddy current losses, induced voltage, some of the stuff that you cannot get in magnetostatic case. And finally, if your system involves some pulse currents or some exponential currents or any kind of current waveform that you can come up with, so that the fields and losses and eddy currents are not perfectly sinusoidal, and well, in that case you would have to use transient magnetic. All of these magnetic solvers have similar applications. They can be used for analysis of electric machines, transformers, solenoids, actuators, eddy current sensing devices. So they have many of these applications can be simulated across all of these three different solvers. However, depending on the specific type of results that you're looking for and the specific focus of your design, you would choose one of these three. Electromagnetic solvers can be also coupled with some other multi-physics or cross-physics analysis. For example, you could have a solenoid with a moving part, and the motion of that part would be constrained by the SolidWorks motion. So you could use this SolidWorks motion to create a spring which is holding this moving part, also damping its motion, and really predict and analyze dynamically how the electromagnetic force given to you by, for example, EMS transient magnetic is going to interact with the SolidWorks motion analysis and give you the full motion result. If we stick to this solenoid example, then the current losses in the solenoid coil are definitely going to raise the temperature of the solenoid, and this temperature can be computed by using coupling to EMS thermal. Some of the parts that form the solenoid could be deflected due to the electromagnetic force, stressing this part. So if you are after this deflection result, if you want to make sure that everything remains aligned properly, then EMS structural would come in handy. So now that we're done with EMS and the overview of different solvers, let's dive into our topic for today, which are magnetic gears. As you probably know, magnetic gears, they don't have any, the only difference between them and traditional mechanical gears is that they use a different mechanism to transmit torque from one end to another. But from the external point of view, that their functioning is the result of their work is more or less the same. They're used to transmit torque from the input to the output, and the only difference is that for in a traditional mechanical gear, you would use mechanical interaction between gears to transmit torque from one end to the other. However, in magnetic gears, the gears are actually formed out of permanent magnets which interact and force one another into motion. The whole idea behind the magnetic gears is not to replace mechanical gears. It's simply that there are some. I mean, mechanical gears are not going anywhere, but there are some applications where magnetic gears would be very useful. For example, some micro electromechanical systems would actually benefit from having very small gearboxes, and those in those cases magnetic gears would actually do come up with a bit higher torque density than mechanical gears. Overall, if we're talking about torque density, then mechanical gears are slightly, depending on type of different magnetic gears, mechanical gears are slightly more densely packed with torque. However, the difference is not that big. So they're more or less similar when it comes to that. However, magnetic gears, they offer higher efficiency because there is no direct interaction between the gears, and that fact itself brings takes out some of the losses associated with tearing and the friction between the gears and so on. Another big thing is low maintenance. You don't have to lubricate the gears, you don't have to change the oil, or they don't break that easily. And another thing which is also important in some applications would be that the isolation between the input and the output. Too much torque is not going to break your system. Your gear might slip, but there is not going to be some serious damage to it, which is a very important thing in certain applications. The big disadvantage of magnetic gears are definitely a higher cost associated with usage of permanent magnets, and more complex structure, and they're in general more difficult to manufacture. Again, all of this depends, it's dependent on the exact type of magnetic gear that you're looking at. At this slide, we have 3 different types, some of the most common magnetic gear types. Going from left to right are concentric, harmonic, and planetary magnetic gearboxes. The planetary gearbox is pretty densely packed with torque. It offers the advantage of having high torque density and 2-stage transmission, but it's, as you can see, it's sort of difficult to hold all these rotating magnets in place and to align, to make sure that everything is properly aligned. So overall, from the mechanical integrity point of view, it's not very easy to manufacture and use these planetary gearboxes. Something similar goes with the harmonic ones. They would require flexible permanent magnets, and in general, this fact is slowing down their implementation. They're not very widely either used or researched. The type of magnetic gears that is actually getting the most attention is the concentric gearbox type, which is the one on your left, and that one is the one that we're going to be simulating today, and that is the one that is getting by far the most attention from the engineering community. So as you can see, there are 3 main components to concentric magnetic gear. The first one would be the inner rotor, or in this case, the high-speed rotor, and then at the outmost position on the outside of the gear, you have of the gearbox, you have the low-speed rotor, the one with multiple, with, like, I think in this case over 40 smaller magnets, and in between these 2 rotors you have a ferromagnetic modulator, which makes sure that the field, for example, coming from the inside, where you only have 2 poles, gets modulated in such a way, it gets changed in a way so that it can interact, so that the field coming from the inside can mesh with the field from the external rotor. So that's the function of the modulator, which is sandwiched between the two rotors. The design we are going to analyze today has a very poor cogging torque factor of about 2. So we can expect to see a lot of fluctuation in our torque profile. So we're actually looking to see if this formula, what it does, the cogging torque factor formula says that if your factor, depending on the number of poles and modulator pieces, is close to 1, your cogging torque profile, actually your torque profile, would be more or less smooth. In our case, we're aiming for a factor of 2, so we're probably going to get a lot of oscillations in our torque for different angles of misalignment between the internal and external rotor. Some of the results we're looking for are, as you can see, field, torque profile, saturation, and we're also going to analyze. We're going to see how change in some design parameters plays out in the field or torque results, and is it getting us anywhere, and how easily it is to evaluate certain design changes in EMS. One more thing is it's important to say that like any other rotating machine, simulation of magnetic gears in their simulation analysis do require a 3D simulation, simply because of the strong end effects and a lot of leakage going on in the front and back side of the gearbox. This is even more true for the magnetic gears, because they have actually 2 air gaps and strong magnets on both sides pushing the flux each other, and it's even more pronounced, this end and 3-dimensional field distribution in the case of a magnetic gear than in the case of some, for example, permanent magnets, IPM, synchronous machine, or brushless DC machine. They have only 1 air gap, and they only have permanent magnets on rotor, or so this end leakage in a 3rd dimension gets even more pronounced in magnetic gear, and that's why it's so important to use 3D simulation. Okay, so now we're going to move into SolidWorks and have a look at our assembly here. As you can see, there are all the parts I have just described. This is the modulator. This is the internal rotor, or the high-speed rotor. And the additional component that is part of almost any EMS simulation is, of course, the Airbox, which allows you to, which is actually a necessary part. This Airbox is filling in the space between the external and internal rotor, and allowing us to allowing the magnetic field to propagate between the two, or even to go outside and into, of course, into the axial dimension, and to establish this leakage flux and this leakage field that I've just introduced on the previous slide. So anyway, all in all, we need to have this Airbox as well, but let me hide it for now. So the type of study we're going to be using today is magnetostatic. However, to get this torque profile, we're going to have to rotate the inner rotor and compute all of the results for each rotor angle. To make all this a bit easier and of course automated, we're going to be relying on EMS parameterization, which easily takes into which can easily manipulate different SolidWorks dimensions and change them and produce results for every case. However, to make different SolidWorks dimensions available to EMS and EMS parameterization, we need to select them. For example, this is here the mate, which is defining the alignment of the rotor. So, and it's defined as an angle between the rotor and one of the SolidWorks planes. So we can just select this dimension, right-click on it, and go to EMS, add dimension parameter. This way, this dimension becomes available to EMS, and EMS can change it any way you please. If another thing that we're going to be playing with is the length of the modulator pieces. That one is defined by this extrude length here, which is by default equal to the length of both outer and the inner rotor, but we're going to change it and see how it affects the overall torque magnitude. So the same thing here, you right click on it and go to EMS and add dimension parameter. That way EMS has control over this dimension and can change it. So the first thing we need to do in every EMS simulation is define materials for each part. As you can see here, we have these 4 parts, and what we simply do is we right-click on the part name and then go to apply material. So for this modulator, we have selected mild steel from the ferromagnetic materials library. For the airbox, we've applied air. For the rotors, however, they both have, let me actually show this inner rotor and hide the modulator. The inner rotor has 5 bodies, and the yoke is made out of the same ferromagnetic material that we've used for the modulators. However, the magnets, for them in the EMS material library under permanent magnets folder, you can find different types of permanent magnets. In our simulation, we went for the neodymium magnet. Defining a magnet is not done until you define also the coercivity direction. To do that, in this case, you just select cylindrical coordinate system and then radial alignment of the magnetization vector. So in this case, since everything is so nicely axis symmetrical, there is no need to create any additional coordinate systems. You can just simply use the global cylindrical coordinate system and define magnetization direction for each magnet. The same thing for the other 2 magnets, with the difference that we're gonna change the direction of the magnetization so that the fields from 2 adjacent magnets does interact and go from one to another, which is what we want to have. Okay. Something similar has been done for the low speed rotor, but with just much more magnets. The final thing before we go to parameterization would be simply to select to define a virtual work and define a part at which we're going to compute the torque. In this case, we're computing the torque on the high-speed rotor. But it doesn't make any difference. I mean, we could have computed the torque also on the external rotor. The torque will just be, the torque difference would just be proportional to the gearbox ratio. Now the parameterization. In the parameterization, you can select design scenarios and check the geometric variable that you want to parameterize over. In this study, we have been working on the torque profile, so the only dimension that we're going to be changing is the rotor angle. So you define the starting value, step value, and the ending value of the angle. So this would be enough. I mean, after this, I would have just clicked run and waited for the results. However, in this case, the results have been pre-constructed, so we have the results table fully filled with values. We also have magnetic field results. So let's have a look at the field results for this section plot here. So this is the B field. We can see that the B field values go all over to over 2.5 Tesla, which sort of indicates that this structure is a bit saturated, and the fact that we have used a linear material indicates that that our torque results might not be very accurate. However, we're going to go to results table and plot and see how do these how is this torque changing with the rotor angle. As you can see, it's changing a lot. It's oscillating by a large value, which is something we have expected based upon the design that we went for and the high cogging torque factor. However, due to the saturation, it would be a good thing to see and compare how would the torque results be different if we have used a nonlinear material with a BH curve and a material which can take into account a saturation in the system. So to do that, we have defined another study which is in all sense equal to the previous one, with the only difference that for ferromagnetic parts we have used a ferrite alloy whose BH curve we can see right here. This material can be found in the EMS material library under the nonlinear ferromagnetics folder, together with bunch of different ferromagnetic nonlinear materials. For each and every one of them, you can see its corresponding BH curve. If you are unable to find the material that you're looking for, you can easily define your own material just by simply importing your text file that contains BH curve coordinates or typing in the values manually. And if you first have a look at the field results, you can see that the field is now much lower. It doesn't even reach 1.5 Teslas. And the torque has also dropped substantially. Actually, let's go back to my slides where I have compared the two torque values, and you can see the torque has dropped by over 30% or so. So it's very important to use if you see that the specific design and the air gap length and the distribution of magnets is such that when using linear simulation you get very saturated field results, then it's probably it would be a very good thing to go back, change it to nonlinear material if you have it, and rerun everything to get much more accurate torque results. Finally, let's have a look at the third study where we have kept the angle constant. However, we have changed the length of the modulator pieces. Let's have a look at them. It would be even more obvious if I hide the external rotor like this, and then animate versus scenario. So then we can see how the field is changing with different lengths of these modulator pieces. Based upon the technical engineering literature, we can expect the peak torque to be for the length of modulator pieces, which is slightly under the length of the rotors, because in that case this a bit shorter modulator is going to keep the flux on the inside of your device and prevent it from going too much into this axial dimension, to prevent it from leaking into the end frontal and rear zone of the air domain in front and back from the gearbox. So the shorter I mean, you cannot keep. This is what we're going to see in our torque results. Is that of course, if your modulator pieces are too short, I mean the interaction between the two rotors is going to be weak. However, before, I think the scenario 6 is the scenario where modulator pieces and the rotors have the same length. However, we are peaking with our torque at the scenario 5, which means a slightly shorter length of the modulator pieces, and that's exactly why it's important to keep them a bit shorter to prevent the field from going outside of your structure, leaking and not contributing to the torque. Another thing that you could do with this with EMS and change in addition to the length of modulator pieces would be their thickness. There is also a sweet spot for the thickness of the modulators, which again you can use EMS and SOLIDWORKS, join them through the parameterization feature, and sit down, relax, and wait till EMS goes over all the thicknesses of the modulator and comes up with the optimal thickness for the maximum torque. Of course, another thing that also would be easily simulated would be the overall arching angle of the magnets. That also can be changed easily through EMS parameterization. So this, I mean, I see that the time is slowly running out. So with this, I would like to close this webinar, and thank you for your attention. If there are any questions, now would be the right time to type them in the chat box, and it'd be my pleasure to answer them. Well, if not, then on behalf of everyone in the EMWorks Montreal office, I thank you for attending today's webinar, and I'm looking forward to seeing you soon on another EMS webinar. Thanks. Have a nice day. Bye-bye.